Okay. Good morning, Professor Bardossy. Okay.
Good afternoon
Yeah, good afternoon to you.
for you.
Okay. Please welcome Professor Bardossy and give him a big hand. Okay. Professor Bardossy, we will see again after your valuable keynote lecture. Okay, 30 minutes. Okay. Okay, thank you.
Thank you.
네, 그 30분간 동영상 강연을 하고 간단히 질의응답 시간을 갖도록 하겠습니다.
Good afternoon, ladies and gentlemen. It is a great honor for me to be here and to present this presentation for you. The contents of my presentation is the following. It's an introduction where I will give a few views of modeling. Then I will speak about problems with measurements, problems of modeling, and then why do we have the uncertainty and where are the real problems, and we will finish with a summary. It is the problem always with measurements and models. We measure a lot of things and very often in incomplete manners, and we have models, mathematical descriptions of our systems. If you look at the following model result, namely the prediction of the appearance of Halley's comet, then you get the result from the astronomist that is it will happen on the 28th of July 2061. But if we ask the question, will there be a big flood on the Hangang River in Seoul in 2022? We do not really know. We are much more uncertain. We cannot tell the date exactly. So this gives us the feeling that hydrology is not doing as well as astronomy. We just do not have the accuracy. We have a lot of uncertainty, and this uncertainty is practically the central point of my presentation today. Why do we have uncertainty? Just a little introduction to this. I think nobody of you ever tried to count raindrops. Now, how many raindrops fall on a small or medium-sized catchment during an event? If we look at Seoul, after Wikipedia has an area of 605 square kilometers, and if we have 12 millimeters rainfall falling in an hour, then this means we have 10 to the power 14 to 10 to the power 15 raindrops. If we put these raindrops in a line, then we get a line which is something like 10 to the power 7 or 10 to the power 8 kilometers, so it is at least 10 times the moon and back. Now, what does this mean? This means that we have a problem. We will certainly not be able to predict or to model or to measure each raindrop. We have to aggregate, we have to put things together, and that is already one of the problems. It's a highly complex system. What do we measure? In hydrology, we measure time-dependent and time-invariant parameters. Time-dependent parameters are precipitation and discharge. For example, temperature we could also take. They are measured at selected locations usually, and the measurements cannot be repeated. If a measurement was not taken, then you will never have the opportunity to take it again. If yesterday you did not measure precipitation, you will never be able to measure it again. These measurements, both precipitation and discharge, are measurable also through remote sensing, using satellites for discharge, altimetric measurements from satellites. So you have at least some kind of high-tech extension of the classical measurements. The other parameters are the so-called time-invariant parameters. Time-invariant parameters are where we think that they do not change in time, or they change only very slowly, like soil parameters, hydraulic conductivities, etc. These are highly variable in space and time, and thus very uncertain because we have only a few observations. Other parameters which are important for our modeling are land use, which is relatively accurate due to satellite images, and topography, which is very accurate nowadays. So we have very different informations with very different uncertainties. Let's have first a look at the uncertainties and the measurements of precipitation. Precipitation is our most important input into our models. We use in Germany the classical rain gauges. The rain gauge has the area of 200 square centimeters. The spatial density is one station for about 350 square kilometers. What does it mean? You try to represent an area of 350 square kilometers with a small area of 200 square centimeters. This shows we have an enormous uncertainty. If we would put all the station areas together, what we have in Germany, which is about 1,000 online short-time precipitation measurement stations, then it would fit easily into a single office. What about the radar? Radar is measuring precipitation indirectly. It's measuring reflectivity, and it has a lot of serious problems. First of all, it has time-dependent error structure. Due to wind and attenuation, the error of the measurement can be at a given location very, very different. We have an additional problem, namely radar does not measure near the ground, but the further you go away from the radar, the higher the elevation is where it measures, which brings in a lot of uncertainty. Then we have the satellite possibility to use satellite measurements, which have discrete overflight times, and at those times they take a kind of image, and in between we use geostationary satellites to fill in the gap between these overflight times. But it's a little bit like that you would try to estimate precipitation by looking out the window 6 times a day for a few seconds. You see, the uncertainty will be very, very high. Now, just to show you the problems of radar measurements, radar is already in hydrology since quite a long time. The radar measurements are problematic both in how much rainfall was falling and where it was falling. Here you see two extracts from radar images for the same area. So this is an intersection of two radars in southwest Germany. And you can see the structure is relatively similar. It is a kind of band structure, but there is a displacement. The displacement is due to the different elevation where the radars are measuring and the wind drift. And the other problem, the more serious problem, is that the values are very different. On the left image, the precipitation intensity goes from 0 to 6 millimeters per hour. On the right image, it goes from 0 to 30. It's about 5 times that. And that is because it captures a different layer of the atmosphere, and this brings us a lot of uncertainty. So we have problems with radar, and it seems that for quite a long time we will have to keep working on this. There is another possibility to measure or to improve precipitation measurements, namely to use so-called opportunistic sensors. Opportunistic sensors are, for example, private weather stations, telecommunication links. So for the mobile phones, you have these telecommunication links, and they are very sensitive to rainfall, and the power what they need for the communication depends on the rainfall intensity, and that's what you can use. You can use also the video recordings and try to find rainfall intensity out of images. So just to give you an impression, in Germany we have about 1,000 rainfall stations which are operated by the German Weather Service, and we have 40,000 private weather stations. These 40,000 private weather stations are all online. They provide information in real time, so they should be used. But they are not really good measurements. They are far from the quality of the German Weather Service stations, so we have to process them somehow. We have to remove the bad measurements, and we have to assign correct values, so we have to make a kind of bias correction for those values, and we have to assign uncertainties to these measurements in order to combine them with others. So the same applies to telecommunication links. I have seen that Korea does not have too many private weather stations, but we sure have a lot of telecommunication links which could provide you very useful information on rainfall. Now, here you see the 3 images for the same rainfall event, which caused a devastating flood on the Aar River. Left, the radar image, in the middle of the interpolation based on the Weather Service data, and on the right-hand side using also the private weather stations with pre-processing. And you can see the images are quite different. In the combined image, you have a lot of details, and you do not miss the real intense part of rainfall. And if you look at this in a table form, you can see that the conservative classical estimation of rainfall for a duration of 14 hours, which was the critical time for this flood, and for the whole area of the catchment was 85 millimeters. Our guess, using also the same information but added the private weather stations, says it was 119, and this is a difference of more than 40%. So we have a very high uncertainty, and we have to try to get the right precipitation. Hydrological models showed that these 130 millimeters are a realistic estimate. Let's have a look at the models. There are a large number of hydrological models, and they are classified very differently. There are physically based models, conceptual models, lumped or spatially distributed conceptual models, and there are nowadays a lot of machine learning models. They all have their advantages and disadvantages. The first question is, of course, which model should we apply? Is there a universally good model? No. Data and the questions what we want to answer with this model should decide on the model selection. The next question is, are the models those which are responsible for the uncertainty? Are models bad, and can we improve them to have very little uncertainty? There is this method GLUE by Keith Bevan, which tries to assign the uncertainty to model parameters. But one thing what we should not forget is that models cannot be better than the data which are used for them. For this, we will look at the precipitation uncertainty. Why is the model failing? Is it maybe because of the precipitation uncertainty? And we know that precipitation is very highly uncertain. It is measured at discrete locations in space and time. And one thing what we often forget is precipitation measurement networks cannot capture aerial extreme swell. Our investigations show that at least in 2/3 of the cases we are underestimating extremes, and in about 1/3 of the cases we are overestimating. It might be even worse. If we use this wrong kind of, or often wrong information in our models, then we try to correct for these errors, and with that we introduce, unfortunately, other errors. Now, our research question, what is related to this problem is there a realistic realization of precipitation so that the model is good? So can it be that the model is good and we should not do so much work on the model? Is it the precipitation? What is the problem? Now, for this, we would like to find realistic precipitation which should not contradict the precipitation measurements. So practically, we would like to do a modeling with our observed precipitation, so that we, in between the observation locations, we some kind of invent this precipitation, but only in between the measurements. At the measurement locations, we leave the measurement values. And these fields, what we are creating, should have the right spatial variability, and they should not contain unusual values, so we should not invent very high values in our images. And we would like to have these fields so that they can explain our discharge. This is a very complex space-time problems, depending on the size of the catchment and the time period. It can contain up to 100 million unknowns with 500,000 constraints. So it's a very, very complex problem. Now, let's see the application of this, and let's see what does this mean for modeling? The biggest flood on the Upper Neckar occurred in 80 and 82 on Christmas. The questions are, was this realistic? Can we model it? And how did it happen? What really happened there? For this, we used a hydrological model, the HPV model, in a spatially distributed manner. We calibrated it for recent observations, and then we applied it with the observations of the year 1882 and wanted to see what happens. Here you see the model performs very well for the present time. The red line is the observed discharge, the blue line is the simulated discharge. So for present, very dense observations, this works very nicely. Now, if we apply the same model with the data of 1882, suddenly we have a big problem. The red line is the observed, the gray line is the modeled discharge. And you will see we had more than 900 cubic meters per second as a peak in observations, and it's slightly more than 400 for the observations. A nice subtle value of minus 0.27, a really very bad model. Now, this is the catchment. The green is the catchment, what we are looking at, and the red points are the observations where we have measured daily data. Then we look at this and we try to concentrate on the 2 months before these events. We selected 24 days with important precipitation, and we wanted to generate precipitation fields which have the following properties. They are equal to the observed values at the observation locations. They have the spatial variability what the observations have, and they can explain for us the discharge. We used a rather sophisticated method which is called random mixing with Whittaker-Shannon interpolation, so it's a very complex thing to do that. We generated even 100 realizations. So every single day, what we considered had 100 different fields, which all looked similar, but were all much better for the discharge. Let's have a look, for example, for 4 out of these 100 realizations. You see they all have a relatively high similarity. They all honor the observations and have a structure which is realistic. And here for another day you have again partly similar fields. And these all, if they are combined together, bring us a discharge which is now the gray line. The model did not change. We just changed the rainfall a very little bit or in between the stations. So we did not change the station data themselves. But this is a realistic thing, and now we can explain this maximum discharge. If we would, instead of that, look and say, okay, the problem is the model. Then we take a lot of different model realizations, model parameterizations, like in the glue procedure, and then you see these gray domains. This is what we get with different model parameterizations, and we miss the peak discharge completely. If instead of that we look at our 100 precipitation realizations, we can match the observations very well. So this means the problem was not the model. The problem was the precipitation, and there is a realistic precipitation which could explain this field. Of course, this example was based on relatively few observations. Now, the question is, do we have this property also for denser observations? For this purpose, we looked at the Tyne catchment and at the Neckar catchment with 3 subcatchments in Germany. We used 2 models, not to say, okay, this is a specific property of one model, and we used the long time period of 20 years. Now we had, for 20 years, for every single day, we had to make a precipitation field, and that is what we did, and this is done by some kind of gradually changing the rainfall. Here you see how the rain is modified, and we always look, does it give a better discharge or not? It's a complicated procedure, and then we look at what happens with the discharge, and here you see blue was the observed discharge, and orange was the classical when we interpolated rainfall, and these colored lines, which are very close to the observed, are the simulated ones where we simulated reasonable rainfall. Okay, if you look at the whole thing from the spatial viewpoint, you can see in the middle the interpolated rainfall, and these are possible realizations now, 8 different realizations, which all look very similar to the interpolation, of course, because the observation locations are kept constant, but they all look a little bit different, and they all look like realistic rainfall. In radar images, you would also see things like that. So it is a realistic rainfall. There is a realistic rainfall which could have generated this discharge. So then we can ask, what is the bottleneck in observation, in hydrological modeling? Are the models or not? And one could say here that precipitation is, in our cases, the most problematic thing. They are the limitations, and specifically for our extremes. Our networks cannot capture the real extremes, and we have to think about how we can improve that, and as long as we cannot improve that, our modeling will also not be really improved. I could tell you a lot of other things also, but my time is more or less over, so I would like to summarize what I wanted to tell you. Incomplete information, incomplete measurements, and incomplete model knowledge leads to uncertainty in hydrology. Uncertainty has to be quantified, and uncertainty is to a large extent due to observations. To some other extent, it is also a problem of the models. And uncertainty has to be reduced. This means we need good observations, we have to use everything what we can, and we have to do this in a scientific manner to improve hydrological models and to get a little bit closer to reality. Design and management for the future will be complicated. I did not speak about climate change because climate change is a huge challenge for us. But if we do not know the past and we cannot describe the past, then it will be a big problem to quantify the changes. And for this, we have to develop tools. And unfortunately, at the end, we have to say hydrology is not the science which can impress with results like astronomy. It is a necessity, on the other hand, and it is strongly linked to decision making. So we have to do hydrological modeling, and we have to try to do it as well as possible. I thank you for your attention, and I'm ready to take questions.